So moving on to sort of the second half of this lecture is really dealing with how we solve type 1 and type 2 problems when we're dealing with solubility. So I want us to still keep thinking about and using the same strategies that we've thought about for these problems. We're going to write a balanced chemical equation. We're going to write an equilibrium expression. We're going to make sure that everything's in the right units. We're going to set up an ice table. We're going to solve for x. So a lot of this is going to be similar to things that we've seen before. Again, what's just going to be different is the chemical equation that we're using to think about equilibria. So just to highlight a couple of hints and tips here that are kind of important and unique to this kind of a problem. When the problem is asking about solubility, what they're really asking for is what is x? What is the value of x from an ice table? So knowing that, if they tell us the solubility in water, think about how that could help us solve this problem. To give you the answer ahead of time, if you'd like to work through it on your own, the Ksp value is going to be equal to 1.96 times 10 to the minus 8th. So take a minute and try to work through this problem on your own, or let the video play for the worked out solution. So we're going to always start these problems the same way we always did. Start with a balanced chemical equation for the chemistry that's going on, in this case the dissociation of a sparingly soluble salt into its component ions. Write an equilibrium expression. So Ksp is going to be equal to the concentration of lead times the concentration of sulfate, and for this problem we want to calculate what that value is. Now, one of the things that we'll see in these kinds of problems is that we might see units that are different from our traditional molarity, and that's okay for these problems that we'll see. For this problem, though, again, we're going to start with no ions from any other solutions initially. So we're asking how much are we making of these? So this is really a plus x and a plus x. So x is going to be equal to the equilibrium concentrations of each of these, and x is really also equal to the amount of lead sulfate that has dissociated. So again, when they ask for the solubility, they're really asking for what is x. And so again, we need to use this information where they tell us the solubility, so it's really telling us what x is. So see if you can finish working through this problem now that we know what the value of x is. Again, telling us what the solubility of lead is really is telling us what x is. So again, with this problem, they give us the units in something different from molarity, but because we know we need to have molarity in order to use and think about an ice table, we need to do some calculations in order to convert this into molarity. So again, some basic unit conversions. We're going to have a prefix unit conversion to convert to liters, and then we need to use the molecular weight here in order to convert into moles. Doing so gives us the concentration of lead, or the solubility in lead of water, as 1.4 times 10 to the minus 4th molar. That's equal to each of these concentrations at equilibrium, and so we're really then just multiplying these two values together to get the Ksp value. So one of the things that we need to make sure that we are very cognizant of as we're doing these kinds of problems is that it's very common to see coefficients that are not equal to 1. So again, some of these that we see up here, there might be two ions that are produced, but again, the anion to cation ratio is 1 to 1, so those coefficients will be 1, and so we don't really need to worry about those there. But we're going to see a lot of salts here that are going to have non-1 coefficients. Make sure that we don't forget these in our ice table, and our next problem is going to allow us to practice that. So, and I've drawn just a little picture here to help us think about this next problem. But again, this is another determining Ksp problem, so a type 1 type problem. So we're going to see a lot of problems here that talk about either forming precipitates or solubilizing something. So again, this problem tells us when lead fluoride is shaken with pure water at 25 degrees C, the solubility is found to be this number. This is kind of related to what the previous problem was telling us, that they're telling us what X is. But this is really sort of what's going on here. You're going to take a large chunk of this lead fluoride and you're going to put it in some water. You're going to shake it up, do all kinds of things. You're going to wait for that solution to reach equilibrium, and some of that lead fluoride is going to go into solution. What you then do is you look at the amount of lead that you have in solution. And again, if we write a balanced chemical equation, we're going to see that that would be equal to X. So once we know the solubility of lead here from this, and we know that that's X, we can do just like we did in our previous problem, and we can calculate what the Ksp value is going to be. The Ksp for this problem is 7.0 times 10 to the minus 8th. So I encourage you, try to pause the video right now and see if you can work through this problem the same way we worked through sample problem 19.6a, and see if you can arrive at the correct Ksp value. So thinking about what's happening here, again, treat these problems all the same. Start with a balanced chemical equation, noting that this time we are going to have a coefficient that is not equal to 1. Write your Ksp expression, making sure to include that non-1 coefficient as an exponent. And understanding now that we're going to multiply the values that we get for these equilibrium concentrations times each other with the fluoride concentration squared, and that will give us our answer, our Ksp value for lead fluoride. So again, nothing is relevant with our solid in our equilibrium expression. We start out with no lead or fluoride from any other sources, and we're going to make X amount of lead and 2X amount of fluoride. Again, they tell us the solubility is found to be 0.64 grams per liter, so they're basically telling us what X is. So again, that tells us what X is there. So if you were stuck getting this problem started, now that you know a little bit more, try to finish it out. So again, just like we saw with our last problem, they give us the solubility of lead, but they give it to us in units that are not molarity. So we need to do a little bit of work to convert 0.64 grams of lead fluoride per liter into a molarity. So again, we can use the molecular weight for that. No need for a prefix conversion. We're already in units of liter. And so we get that the solubility, now we'd call molar solubility, is 2.6 times 10 to the minus third moles per liter. So that's equal to X. So we know that that is going to be the concentration then of lead at equilibrium. But just kind of looking at this unit conversion down here, this helps us again understand that we've got sort of a molar ratio that we need to have that allows us to have twice as many fluoride as we do lead. And so this needs to be multiplied by 2. And ran out of room here to finish out this problem. But again, this concentration is going to be equal to 2.6 times 10 to the minus third. I have to double it to get the fluoride concentration. And then to figure out my Ksp, I actually have to square it. So if this problem was just asking for maybe the fluoride concentration, it would just be double this value. And again, doubling that value in either units. But to get our Ksp, we need to put the lead concentration in, 2.6 times 10 to the minus third. This number is doubled to get the 5.2 times 10 to the minus third, but then we also have to square that for our Ksp. So that's how we get our 7.0 times 10 to the minus 8th. All right, moving on to a few type 2 problems. So calcium hydroxide, another one of these species that's sparingly soluble. Again, a little bit of a backstory here. It's a major component of mortar, plaster, and cement, and solutions of calcium hydroxide are used in industry as a strong and inexpensive base. Okay, so it says calculate the molar solubility. This is just another one of those clues. If something says, what is the molar solubility? They're basically asking you, what is X? So again, calculating the molar solubility of calcium hydroxide in water, they give us the Ksp, so this becomes a very typical kind of problem that we'd see previously. So kind of giving you the answer here so that you can try to work through it on your own. The molar solubility here is going to be 1.2 times 10 to the minus second molar. So that's the answer you should be getting. So pause the video and see if you can work through this problem on your own. Again, if you're getting stuck knowing where to start, always start out the same way. Write a balanced chemical equation for what's going on. Write an equilibrium expression. And again, this time they gave us the value of Ksp because we want to solve for equilibrium concentrations. Set up your ice table. Again, we're only going to have products appearing in our ice table. So this is going to be plus x plus 2x. Remember, those coefficients matter here. So x and then 2x. Now this is another point we have to make sure that we don't lose some important information. The Ksp value is going to be equal to x times the quantity 2x squared. Make sure that you just don't write 2x and then the squared by the x. That 2 applies to both of these species. So this ends up being the quantity 4x cubed equals our Ksp value. Okay, so a classic place that students make mistakes is not making sure to either include that exponent or to distribute that exponent to both the coefficient and the variable. Okay, so having 4x cubed equal to this, little bit of algebra that we probably haven't seen yet, we're going to divide both sides by 4 to isolate the variable by itself, and then we need to take the cube root. So make sure that you know how to do both of those in your calculator. Solve for x, which is 1.2 times 10 to the minus second, and remember, solving for x is solving for the molar solubility of calcium hydroxide. So just a little heads up, another way that you might see this problem is you might be asked, what's the pH of this solution, right? So if we think about that, then we'd need to solve for this concentration. It's going to be double what x is. So 2 times this value will be the hydroxide concentration, and doing our around the block could figure out what the pH is based on that hydroxide concentration. So our next sample problem is going to actually build on a sample problem that we've done already. In sample problem 19.7, we calculated the solubility of calcium hydroxide in water. So basically asking if there's nothing else in that water and calcium hydroxide is allowed to dissociate to whatever extent it's going to, what's the solubility of that going to be? So we build on this and we say, well, you know what if we added 0.1 molar calcium nitrate to solution? Again, if we've added calcium nitrate, we have to remember and think about the fact that that's going to be adding calcium ions to solution and nitrate ions to solution. Well, nitrate ions are going to be spectators, so that's not anything I need to worry about. But if I'm adding extra calcium ions already there, if I'm filling up that bucket already, if you will, with calcium ions, hopefully based on our previous discussion, you should be thinking that the solubility of calcium hydroxide is actually going to go down if we've got a common ion that's there. The question is, though, how much? So remember, when we have a problem that says, what is the solubility, that's really asking us, what is X in our ice table? So knowing those few pieces of information, see if you can work through this problem and get that X, or the solubility, is going to be equal to 4.0 times 10 to the minus third. So go ahead and pause the video and see if you can work through this modified version of sample problem 19.7 now when we've added a common ion. So treat all these problems the same. So again, we're going to have an equilibrium here that allows calcium hydroxide to dissociate into calcium ions and then hydroxide ions. What is different now is we are already filling up our cup of calcium ions by adding calcium nitrate. And because calcium nitrate is completely soluble, this is a one-way arrow, the concentration of 0.1 molar calcium nitrate means we've also got 0.1 molar calcium ions. So that's where that piece comes from. No other sources of hydroxide. Then our ice table continues in our change column like we'd expect. We've got plus x and then plus 2x. So now this is going to be 0.1 plus x and then 2x. So now that we know what these values are, and again, they give us the Ksp, how do we go ahead and solve for x there? So what we're going to see here is we're going to do the same type of things that we did in previous problems where we wanted to simplify our algebra. So again, we've got 0.1 plus x and then the quantity 2x squared. That's going to be equal to 6.5 times 10 to the minus 6th. Now, if we had to go through and kind of factor all of this in, my goodness, we would have, some complex algebra. So let's see if we can make a simplifying assumption that x is going to be small. If x is going to be small, 0.1 plus x simplifies to 0.1, and now all of a sudden this again becomes manageable algebra. Go through and solve when we get that x is equal to 4 times 10 to the minus 3rd. I just want to flip back for a second and highlight 4 times 10 to the minus 3rd. If we flip back here, 1.2 times 10 to the minus 2nd. We got a smaller number, which is what we predicted. We predicted that the solubility would go down, and that is absolutely what happened here. Solubility went down. The rest of this problem just kind of goes through and says, you know what? What if we wanted to actually calculate what those solubilities were? Okay, that we would just put those values of x in to calculate what the calcium and then hydroxide concentrations were. This is just a little note. If you happen to watch the video that's online for this, I believe there's a slight error on the video in terms of just reporting what this number is, but everything else is totally fine with that. But again, this could be a problem where I could ask you, what's the pH of this solution? And if that's the case, you'd have to take this hydroxide ion concentration and use that to determine pH.